Welcome to the next video in the real analysis video series, and in the last video we basically just concluded that the real numbers exist and they have they satisfy all the axioms, and so from now on we just get to assume and use the fact that the real numbers exist and have satisfy all of those axioms. So we get to use the important upshot of all of that is that we get to use those axioms in proofs. Okay, great. So first theorem, there is only one real additive identity, right? So effectively this number 0 that was introduced in the axioms, we're going to prove that there is no second additive identity, right? You couldn't have this other thing, I'm going to call it 0 prime. You can't have a distinct 0 prime which is also an additive identity. There has to be only one. Well, how do you prove such a thing? Well, you basically say, assume that this thing exists, that this other additive identity exists. But then what you do is you prove that it must equal the first additive identity, right? If they equal each other, then there really just was the one. So that's what we're going to do. Okay, so again, the idea here is that we assume the existence of another additive identity and prove that it must equal 0. Okay, how do we do that? By the additive identity of 0 prime, we can start by writing down 0 and say that that is the same thing as 0 plus 0 prime, right? I mean, because after all, what do we know about a thing that we call the additive identity? Well, I guess actually, am I starting from the additive identity of 0 prime or 0? Well, in any case, if you start from 0, let's just say it this way. If you start from 0, then what we know about 0 is that, what am I saying? Yes, of course, this is the additive identity of 0 prime, because what I am saying is that if you take my first 0, this 0, and add to it 0 prime, because 0 prime is an additive identity, that means that when you add it, it leaves the number alone, right? This is using, right here, this is using the additive identity property that we are assuming for 0 prime. So that's that move right there. But now that we have that, okay, then we just use it again, but then we use the additive identity property of 0, saying that if you take 0 and you add it to anything, then you don't change it, which means that 0 plus 0 prime must equal 0 prime as well. Okay, and so that basically concludes the proof, because after all, that just means that 0 equals 0 prime, and we're done. Write the Halmos. I love that that box is called the Halmos. That's such a kind, sweet memory of the mathematician Halmos, for whom it was named. So that's great. Okay, let's go on to another theorem. Unique negatives. So the claim is that if x is any real number and negative x prime is an additive inverse of x, then they have to be, right, again, they have to be equal. There can only be one, right? Just as there is only one 0, if you give me any x, it has only one additive inverse. So if you wrote down a second one, then it must equal the one that we name by minus x. So there can only be one, right? We're proving that the additive inverse is unique. There is only one of them. And again, right, how do you do that? You assume that there are 2 of them and prove that they must be equal. Standard way of proving uniqueness, or standard way of proving that there is only one of something. Okay, how do we prove this? And I'm going to prove this slightly differently than how Zorich does. Zorich has the better proof in the sense that it's much cleaner and more elegant. I'm going to give a proof that I feel like maybe kind of springs to mind a little bit easier, so that this is a little bit gentler for a student new to the subject. And so how am I going to get this proof started? Well, I want to write down what we know about the additive inverses. Oh, and this should not be identity, this should be inverse. Oops. Anyway, what we know about an additive inverse, like negative x is that if you add it to x, you get 0. So I'm just going to write it down, right? This is often a proof strategy, which is when you don't know what to do, just write some stuff down, right? And so I know I can write that down. And likewise, since negative x prime is another additive identity of x, then I can go ahead and say that x plus negative x prime also equals 0. So that these two things are equal to each other and equal to 0. Okay, and now what I want to do is I effectively want to, in a certain sense, add or do some kind of a canceling, I suppose. So let's start by thinking about what if I took this thing, or maybe even think of it like this. What if I took this equation, right, just the left portion of the equation, and said that this x plus minus x is equal to 0. But then that means that since these two are equal, and then I can substitute them, right? So basically what I'm arguing is that I get this equation, right? So you can kind of say that like, well, look, if I have this object, I can replace this part of it by 0. So that might be a good way to explain what's going on here. And when I do, a few things happen on the various sides. So one thing is that right here, this becomes just negative x. Honestly, it occurs to me, this could have been, I could have streamlined this, and maybe that actually would just get me Zorich's proof. But let's ignore this and say, look, let's just start. Not that it's wrong, but that I think there's a better proof than what I've written down there. So anyway, let's save the Halmos for the end. So let's write down minus x. I'm trying to prove that this minus x is equal to minus x prime. Well, I can add 0 because we know that that's how 0 works. And I am trying to work into this picture x minus x prime, right? Like I would like later on to show that this is equal to minus x prime. So if I'm trying to get minus x prime into the picture, then maybe I take this 0, which I know is equal to this, and I do a substitution. So I say that this is minus x plus minus x prime. Okay. From here, we can use the associativity of addition to just ignore parentheses, right? Basically, associativity means that where you write the parentheses doesn't matter. So in a way, that just means you can drop them. And then I can choose to focus on grouping these two together. So this is justified by associativity, but basically I'm just emphasizing that I'm going to add these two things to each other next. And this just means taking negative x and adding them together. And we know by definition of the additive inverse that that means we get 0 plus negative x prime. Okay. And then we know that 0 plus anything leaves it alone, and therefore this is the result, which is exactly what we wanted. And now, Halmos, we're done. We proved that negative x is the same as negative x prime. So there we go. So I've been somewhat disciplined in writing parenthesis minus x like that to denote the additive inverse, but we are used to the idea that adding a negative is the same thing as subtraction, and so we might as well adopt that as an official policy from now on, that this and this just mean the same thing. And by the same token, rather than writing AB inverse like we would with our official notation about multiplicative inverses, we agree that that really just means the same thing as A over B. And in particular, that B inverse is the same thing as 1 over B, where A is equal to 1. Okay, anyway, so that's just a little note about notation, not actually a deep or interesting point. This might be a bit of a long video, so maybe this is a good time to pick the rest up in the next video.